So we just learned about Ernest Rutherford's experiment, which showed that an atom is made primarily of space. In fact, you have a very small region of positive charge with negative charges moving all around it. Everything else is space. Everything is space. Okay, so the problem with this model of the atom was that we were able to see that certain wavelengths of light could be seen when a gas was excited, but not all wavelengths. And Rutherford's model of the atom didn't really explain that. So for example, here, this is hydrogen gas. All of these wavelengths are given off by electrons that are excited in a hydrogen atom. Now, visible light, you've got this region here, a visible light. This is where you'd have your red light and your blues, and then a violet over here as well. Okay? So we can see this light, but what about all these gaps? What describes these gaps? So Rutherford had a brilliant student by the name of Niels Bohr who proposed a solution. He said, well, this can be explained using the new field of quantum physics. We knew by this point that if you took an electron and you could lift it to an excited state and then drop the electron to a less excited state, it would release a photon. Great. The problem was that any number was possible still. But Niels Bohr came in and said, no, with an atom, you can have some lower energy value or some upper energy value, and the electron is going to jump between these two. You're not going to have an electron stop part way. That's not going to happen. So you take an electron here, you excite it, say, put it in a tube and apply a voltage to it. That's going to excite the electron, jump it up to some higher energy level, and then when that electron loses the energy, it jumps back down and it releases a photon. And there's no partial jumping. That's not possible. It has to be a certain quantifiable number, therefore the energy states for atomic electrons have to be quantized. Alright, so how did he prove this? Well, he found that angular momentum was also quantized. In other words, angular momentum, which remember that was just, you have an object that's spinning, and the angular momentum is the momentum of the rotation. Well, in this case, we have an electron that's spinning around some positively charged nucleus. So it has angular momentum. But its angular momentum was a multiple of some constant number. The equation's not important. The important thing is that it's a whole number multiple. It's a quantized number. So we're dealing with quantum physics here. Okay, so he discovered this and he found the equation to show the quantized energy from one energy state to another. And here's how he did it. He looked at the orbit of an electron around a nucleus, positively charged nucleus. The electric force, remember, is Q1, K times Q1 times Q2 divided by their radius squared. That was from our first chapter in electricity. Well, the electric charge of a nucleus is going to be Z times E. Z is the atomic number, which is just the number of protons. We know that now. It was still being discovered then, but we know that now. So the atomic number is the number of protons. Each proton has the positive charge of an electron. So if you have carbon, which has an atomic number of 6, that means it has 6 protons in the nucleus. Therefore, the positive charge in the middle is 6 times the charge of an electron. So there's your Q1, the atomic number times the charge of an electron. Q2 would be the electron itself, so just the charge of one electron, and divided by r squared. Well, the question is, what is that r? The weird thing is that this r is different for each energy level of a particular atom, and each energy level's radius changes from one atom to another. So R1 for hydrogen is not the same as R1 for helium, or for lithium, or for boron, or oxygen, or magnesium, or gold, or whatever. Every atom has a very different R1, and a different R2 and R3, and so on for each energy level. And similarly, we find that the potential energy, which is negative QV, would come out to be this equation here. But we have the problem here of having our R, and that would just be a lot of work to find R for every single atom and every single energy level of every single atom. Thankfully, we have a shortcut. Niels Bohr found, from all of his experiments here, that the radius of the nth energy level is going to equal the energy level number, n, squared, times the radius of the first energy level. So R2 is going to equal 2 squared times R1, or 4R1. And R3 is going to equal 3 squared times R1. So R3 is going to equal 9R1. Awesome. Using this, we get a ratio Rn over R1, that's equal n squared. And using this ratio, we can completely eliminate the need for a radius. Now, I'm not going to get into the full derivation, but what it comes down to is that the energy at the nth energy level is going to be negative E1, energy at the first energy level, divided by n squared. So now it just comes down to, well, what's this E1? Well, for hydrogen, we find that that is 13.6 electron volts. And so our equation becomes the energy at the nth energy level is negative 13.6 electron volts divided by n squared. Now, two things I want to bring up here. First, the minus sign. Second, this is only hydrogen. How do we apply this to all atoms? Well, let's start off first with the negative sign. Let me explain that. Think of it this way. You have an electron way out there, free electron, not associated with any atom at all. Then all of a sudden, it comes close to a hydrogen nucleus. It gets attracted. That energy is pulled down to the E1 energy level. As it does this, it releases 13.6 electron volts worth of energy. Awesome. Well, what if you have another free electron over here? And it gets caught, but it only comes down to the R3 energy level. Or not R3, N equals 3 energy level. Then it's also going to release energy, but that would be E3, which would be 13.6 electron volts divided by 3 squared, divided by 9. So 13.6 divided by 9, and that's how much energy is released by the electron as it falls to the n equals 3 energy level. Okay, so that's what the negative sign really is indicating. But now our second question is, this is for hydrogen. How do we make this work for all atoms? Well, it turns out that it's very easy. All you have to do is multiply by the atomic number squared. So for helium has an atomic number of 2. So to find the energy levels of helium, we would just take those of hydrogen and multiply each one of those by 2 squared, or 4. Oxygen is atom number 8. Has an atomic number of 8. So take this equation, multiply it by 8 squared, or 64. Makes it really easy for all of your atoms. And so there's your all-inclusive formula there at the bottom. All right, now, it turns out that this really is a great model to depict the energy of an electron. We still use it today. It really is a fantastic model. But it isn't what actually is happening. You don't really actually have electrons sitting here whizzing around in orbits like a planet around the sun. No, that's not what happens. Really, electrons can exist anywhere in a region that we call an electron cloud, which has some hypothetical radius in that nucleus. Or sorry, not in the nucleus, a radius for that, for the average of that electron cloud. Now, we could say, well, we just have this round region here, and the electron's somewhere in that round region. Well, that's great, except that it gets more complicated than that. For the first 4 elements, yes, the electron can appear anywhere within this spherical region. But once you get up into other atoms, such as boron, carbon, nitrogen, oxygen, aluminum, so on, all of those atoms, the shape of the orbit itself is going to change a little bit. So for hydrogen and helium, your electron is going to be somewhere in that region. For the next 2 elements, elements 3 and 4, 3 is lithium, and 4, sorry, I've got that, beryllium, that's what it is. I'm giving away a bit of the lecture, that's okay. Lithium and beryllium, the first 2 electrons are going to be in that lower sphere, but the next 2 electrons are going to be somewhere in this outer sphere. Once you get to boron, boron is element 5, so you have 5 electrons. The first 4 appear in those spheres, but the 5th one ends up being somewhere in this hourglass type of shape. And it gets more complicated than that. When you get into nitrogen and oxygen, it's going to be somewhere in this donut shape. What's going on? I'm not going to get you into this because this is advanced quantum physics. This is statistical stuff. It's really crazy. But here's a chart showing many of the different energy levels. With the S energy levels, the first energy level, you're just going to have a small sphere. Second energy level, a larger sphere. Third energy level, an even larger sphere. And since they're spheres, we call them S orbitals. Once you get into the p orbitals, they change into these hourglass shapes. D orbitals are double hourglass shapes. F orbitals are triple hourglass shapes. And double donuts or triple donuts or whatever. You can see here it gets pretty complicated. So let me just finish up this segment of the course, and thus the whole course overall, by introducing the periodic table. You have hydrogen and helium. 2 electrons in helium, and their electrons have to be in a certain electron cloud that looks like a sphere. Lithium and beryllium have 3 and 4 electrons. The first 2 have to be in a small sphere. The next 2 have to be in a larger sphere. These are the actual positions of the electrons. They don't have to be on those lines, remember, but those are regions where the electron can be found, electron clouds. Remember, looks something like this, or like this. All right, once you get into the p orbital, boron, carbon, nitrogen, oxygen, fluorine, and neon, they end up, those p orbitals are something in an hourglass type of shape. Then you get into sodium and magnesium. These are going to be in some 3rd level spherical orbital shell. By the way, we call these s orbitals. These are p orbitals. we get back into an s orbital, and then we get into some more p orbitals. And I'm not going to go crazy with the diagram here because it starts to get really complicated. So we have 1s, 2s, and 2p. The first energy level, you can only have an s orbital. Second energy level, you can have an s or a p. You fill the s first, and then you fill the p. Third energy level, you can have an s or a p or or a d energy level. But before the 3d energy level is filled, it actually fills the 4s energy first, and then you go to 4p and so on. Okay, great. I hope I haven't confused you yet, but here's my point. Here's the periodic table. This is your first energy level. There's your 1s orbitals. And then here's your 2s, where you can have a second energy level. And the next, you start filling these hourglass-shaped p orbitals right there. That's these atoms right here. And then after that, you fill the 3s orbital. And then you fill the 3p orbital. There's the 3p right there. And then before you fill in the 3d orbital, you do the 4s orbital. And you get into the 3d after that, which this was the double hourglass shape, something like that. And then you get into 4p, 5s, and then you actually get into 4p, that should be d, 4d, 5p. And you get into 6s, and then before you get into 5d, you get into 4f. And that goes right here. And then you have your 5d orbitals, and then your 6p. All of this whole order is because 4s takes less energy than 3d. The 4s orbitals are lower in energy than the 3d orbitals. 4f is lower than 5d, which is lower than 6p, so on. Hopefully that kind of gives you an introduction into why the periodic table is constructed the way it is. It's all because of these orbital shapes, these electron clouds, and the way the electrons are organized, which was initially introduced by our good friend Niels Bohr. So that is it. That finishes up the section on quantum physics, also finishes up the course. Hopefully you found all this interesting. This last bit on the electron cloud, from here on, you don't need to worry about anything here. This is not going to be on homework, not going to be on exams. It's just fun to learn. It's just fun to see how all this works and how it all fits together. Something you've seen as a child, how it's organized, how it's put together. That finishes up again the section, so if you have any questions, please feel free to contact me. I will be happy to answer any questions you might have. Have a good one.